see it. Now I see it. Okay. Sorry.
No problem. Okay, I could not hear you in the beginning, so I think everyone can see my screen now. Is this correct?
Yes.
Okay, thanks. So today I want to speak about the fundamental theorem of tropical partial differential algebraic geometry. Very long title, but it somehow should continue on the talk given by Sebastian previously, namely to give the right intuition for Newton's lemma in the case of differential equations in the tropical setting. Okay. So here are several references which might be useful later, but okay, I will skip it here. So beside this motivation, there is also another one, namely that if you have a system of partial differential equations, this cannot be checked whether there exist some formal power series solutions of such systems or not. This is proven, for example, by Denef and Lipschitz. So already the existence of such solutions cannot be decided. And the goal of the whole work was to have a better understanding and derive necessary conditions on the support of solutions. Here is a short overview of my talk, but I will just jump into the talk. So we have seen already a little bit about the Newton polytope in the previous talk. So it is defined as the convex hull of a given set X. So we have here just integer coefficients and integer components, sorry. And then we add here this set and take the convex hull of it. And we also speak of a vertex if this point lies on the boundary of the Newton polytope, and it's really essential. So if you would remove it from the set, the Newton polytope would change. And we call this element here the set of vertices. So here is an example which should illustrate this. So we have this 4 points given, and then we draw the Newton polytope. Then we take the convex hull of it, and it's can easily be seen that A2 and A3 can be removed, and the Newton polytope does not change. But if A1 or A4 gets removed, it would change. So the set of vertices here is A1 and A4. And here we have two properties of the set of vertices. So it's a generating set for the Newton polytope, and two vertex sets are equal if and only if they have the same Newton polytope. From this, we directly get that the vertex set, the set of vertices, is the least set generating the Newton polytope with respect to the inclusion as ordering. Okay, so we have defined the set of vertices, and now I define a map, also called vert, sending a set to its set of vertices. And we define two operations on them, namely an addition and a multiplication. The addition is defined as taking first the union and then apply this vertex map, this projection to the union. The multiplication is defined as taking the set addition, so the Minkowski sum, and then apply this vertex map, because in general, this result here on the right-hand side, without applying this vertex map, would not be a set of vertices. And we denote by this capital TM all vertex sets and these operations. So we have here another example, the set X consisting of those 2 points and Y of those 2 points. And we want to perform here this addition. So first, we take the union of all the 4 points and then take a look which elements really contribute to the Newton polytope. What does the vertex map do? So removes this 2 inner points. The result of this addition is 2, 0 and 0, 2. Now we take a look to the multiplication of these 2 sets. For this, we consider X, the elements in X, and 1 element in Y. Then we shift these 2 points by this element. Now we take the second element in Y and shift the elements in X again. So we get those 4 points in total. And now we take a look what happens if we apply the vertex map. These 3 elements remain. Okay, so now we have seen an example for this addition and multiplication. And it can be relatively easy proven that this algebraic structure is a commutative idempotent semi-ring. So it does not have additional inverses. Okay, and as already Vincent mentioned, the support of a power series, here it's a multivariate power series, is defined as the coefficients which are non-zero. And now we can apply the support map. So again, I call the map support, which sends a power series to its support, and then the vertex map. And the result we call the tropicalization map. So it sends a multivariate power series to an element in Tm. If m would be equal to 1, the ordinary case, then this would correspond to taking the minimum of the support set. This tropicalization map is called or fulfills the properties of a non-degenerate valuation. This is a slightly more general notion of valuations. So here are listed the properties. It basically says that it behaves extremely well with multiplication, but not so good with addition. But this is also somehow what we expect, because this Tm, the set of vertices, there we do not have additive inverses. So this is somehow, yeah, the analog here. And these properties are still good enough to prove a fundamental theorem in this, tropical version of partial differential equations. And the first big step for doing this, for proving this fundamental theorem, was to find exactly this tropicalization map, which behaves well enough. Okay, so far we have seen how to deal with multivariate power series in the tropical world, but now we also want to take account of the differential operators. Okay, so here we have given a differential operator simply using the partial derivatives, and we use here this notation of theta j, which makes it easier to read. And we define the tropical analogon of this on a support set S by doing a shift in every component as many times as we take derivatives. And if we would go to the negative, then we withdraw this. This somehow represents, if you take derivatives of a multivariate power series, for example, G1 many times in T1, then it would be a constant in T1 at least. And if you would take an additional differential, you would a partial derivative with respect to T1, then the summand would disappear. So this is exactly what is written here. And this is also why we have this equation here. So if we would take the support of differential operator applied to a multivariate power series, this is the same as applying the tropical differential operator to the support of this power series. So here is a short example. We have here this phi given as T1 squared, this here. So the support can easily be read off. And if we differentiate one time with respect to T1, we get 2 times T1 plus T2. The support of it is written here. And it's equal to taking the tropical differential operator directly applied to the support. Okay. And from a differential operator, it's not that far anymore to a differential monomial and a differential polynomial. Here we have differential operators applied to indeterminates xi, and yeah, they can be multiplied. And the tropical analogon is simply obtained by exchanging the multiplication and the differential operator. And if we allow also coefficients, multivariate power series coefficients alpha, then they have to be tropicalized. Remember, this is taking the support and afterwards the vertex map. And additionally, we have to replace the addition by the tropical version. So here it's an example. So you can see, just replace everything by the tropical analogon we have already defined. And now the question is, what is a solution of a tropical differential polynomial? So having given such a polynomial, tropical one, then we speak of a solution if for every vertex applied to a support set S, then there must be 2 different monomials in this tropical sum, which corresponds to this or which contributes to this vertex. So this looks a bit strange, but if you're familiar with tropical algebra, then I think this is not a big surprise. And if you are more familiar with differential algebra, then you can think of this corresponds to cancellation. So for canceling terms out in the sum, you have to have 2 monomials which cancel out. And now the question is, can we find the relation between the solutions of the original differential equation and the tropical analogon? So here is an example. We have a very easy usual differential polynomial P, and the solutions can be computed easily. So it's just C times T, where C is an arbitrary constant. The support is either equal to 1 or the empty set. So if we tropicalize P and take, so this is here, and I have also included the other representation by the vertex maps, the Minkowski set sum and the union, if you like this more. But as you can see here, on this monomial here, you always shift by 1. And here you just take the vertex of S, because it's the ordinary case, this is equal to the minimum. Okay, so if we assume that we have a solution S of this tropical polynomial with 0 vertex, then it has to be in both monomials. But here we always shift by 1. So this cannot be the case. And yeah, so this is not possible. If 0 is not in S, then we always have this equation. So if S starts with 1, 2, 3, and so on, this in both summands we have a contribution. Also, if this S starts with 2 or 3 or whatever. So basically it says this equation that we do not have any more information from just considering P, or the tropical analogon. But we can also take a derivative in P with respect to T. So then we obtain this single differential polynomial. In fact, it's a monomial. And here, the interesting thing is, for being a solution of the tropical version of it, you always need at least 2 contributions, or none, which means that this here always has to be empty set. So the only possibility is that J contains 1 or is the empty set. So this can be called trivial solutions of this tropical polynomial, or monomial if you want. And this is exactly what we had in the very beginning by studying P and the usual setting, the differential algebra setting. But what we have here is that the solution set of the tropical versions of P and its first derivative gives us the support set of the solutions. But this is interesting. Previously, we just had to take a look to P, but in the tropical analogon, we have to take a look to P and its first derivative. So, in fact, this comes that we have to take differential ideals. This is a usual ideal, this ring, but it also, if an element is in the ideal, also its derivatives have to be in it. Okay, so we start with such a differential ideal with coefficients and an uncountable algebraically closed field of characteristic 0, and it allows multivariate power series coefficients, and also x, y up to xn and its derivatives. Yeah, so that's not a surprise. But the nice thing is that it does not matter if we take the support of the solutions of the usual differential ideal, or we tropicalize the differential ideal and then compute its tropical solutions. We have here a set equality. Remember, from the undecidability result, we cannot expect that we can fully algorithmically understand the right-hand side, because we would have here this set equality. But in some problems, this right-hand side has computational benefits. Also in theory, there, I assume, are very interesting application methods for this visible, but so far we did not figure them out fully. For the proof, one implication is relatively easy if everything is defined, let's say, correctly, or defined as we did. The other side uses an ultra power construction. So yeah, this is very technical and non-algorithmic. and it's also used in the paper of Denef and Lipschitz. And recently we have generalized this approximation theorem in Denef and Lipschitz work to some algebraically closed field, which has countable dense degree over the field of definition, whatever this is. So this can be slightly generalized. Okay, so in this example previously, we have seen that if we have a single differential monomial, the solutions are relatively easy to compute. I mean, they're just the trivial ones. And recently we tried to take advantage of this. And this corresponds also to Newton's lemma somehow of the previous talk, because we define the initials here, but yeah, they are not the same as in Newton's lemma, but there are some relations, let's say it like this. So if we have a multivariate power series A, then we restrict this power series to those terms contributing to the set of vertices. So for example, if we have A given as this, and there could be many more terms, infinitely many, all of higher order, then the restriction would look like this. So if you remember in the Newton polytope, this would correspond to 2, 0, this to 1, 1, this to 0, 2. So this term does not give any contribution in Newton polytope for the edges, for the vertices, so we omit it. And also all higher order terms as well. The nice thing about this restriction is it has just finitely many terms, finite information. And similarly, we define the initial of P, so P is a differential polynomial here, by just keeping all these terms contributing to the vertices. If we apply the tropical version of P to a support set S. So this is basically what is written here. And we take the restriction of all the coefficients. Yeah. So this is slightly different also to some other works, for example, from Hu and Gao. And this is a finite sum, as I already said, and it keeps exactly those terms contributing to the vertex sets. Okay, but it's sufficient for studying solutions to consider the initials. Again, we have to move to ideals. So if we have a differential ideal given, then we define the initial ideal of it as the algebraic ideal generated by all the initials of elements in sigma. Sorry, this should be a sigma instead of G. Again, this is hard to compute. But, okay. Sometimes you can find representations for this, and it's really important that we take the algebraic ideal and not the differential ideal, because taking derivatives and computing initials does not compute. And with this notion of initials, we can extend the fundamental theorem by taking a look to those support sets where the initial does not contain a monomial. So as you saw, if there is a monomial, it only has trivial solutions. And because we are taking a differential ideal, you can shift this trivial solution such that no solution will be there anymore. Okay, and the proof of it is just a careful analysis, rewriting things, and yeah, checking all definitions, and this can be done. Okay, so there's also several works how to generalize this notion to other things, for example, the initial degeneration, which we will see in the talk of Christian Garry. Or, for example, defining bases, Gröbner bases, tropical bases. And another work for the future would be to study all these things if the base field has positive characteristics. Okay, so that's all I wanted to say, and thanks for your attention.
Thank you. Questions?
Can you try to say something more than just the initial term? Or just in some way delete the initial terms and look for the next ones?
So of course you can always do this, and you can build up somehow a tower of it. So far I did not find any let's say application of it or something like this, but yes, it can be done, and there might be some interest in it, but so far I did not really study it closer. Yes, but thanks for remembering me.
Thank you.
I have a question. Could initial and boundary value problems enter into this picture?
You can, for example, restrict the support. This would correspond to saying that, for example, the solution at 0 should be 0 or non-zero. And in this way, you can restrict the problem a little bit. So frankly speaking, it makes it a little bit easier even, but you can do this, yes.
Thank you. Other questions?
So maybe I give one remark, because yeah, I listened to Santa's talk. We also thought a little bit of using exactly her definitions, or let's say to use her definitions and unify it with our definitions. But so far, we did not really were able to prove the fundamental theorem in somehow a mixed definition. So this might also be a work for the future to understand why this does not work so well, and yeah, or maybe we just did not find the right way to do it yet.
Interesting.
All right, thank you again.